Back when I was a kid, we were promised lots of things. We were going to have flying cars, and we were going to have cities in space. And that's not all. In a comic book that cost just a quarter, you would find ads where we could buy some very, very high-tech gadgets that would let us see through things, the very awesome X-ray specs. And although the laboratory director might get mad at me, I'm ready to share highly classified technology being developed at Fermilab that's kind of making these X-ray specs a reality. Let's face it, being able to see through things makes a lot of jobs way easier. Back in 1895, German physicist Wilhelm Röntgen discovered X-rays. Using them, he was able to image, among other things, his wife's hand. And just a couple of months later, British physician John Hall Edwards used X-rays for the first time to guide a surgery. But as useful as X-rays are for looking through smaller things, they don't work for bigger ones. I mean, suppose someone wanted to look inside a mountain or perhaps one of the pyramids in Egypt. X-rays don't work so well there. For that, a new technology needs to be developed. And that's where particle physics comes into the picture. If we can find a particle that can penetrate a lot of matter, we can exploit that to look inside big things. If we look at the known subatomic particles, it turns out that one of them fits the bill. The muon is essentially a cousin of the electron. It's much heavier than the electron, and it lives for a bit over 2 millionths of a second. That's very short, but it's long enough. However, most importantly, it interacts with matter fairly weakly and in very predictable ways. A little bit later, I'll tell you where we can get a supply of muons, but first let's talk about how muons move through matter. When they do, they shake the atoms of the matter as they pass by, sometimes even knocking off the electrons off atoms. These interactions make the muons lose energy, and the energy loss is quite predictable. The energy loss depends on material with more energy loss in denser material. Basically, muon energy loss is like skid marks made by skidding cars. If you're traveling at high speed and then slam on the brakes of your car, you'll leave a skid mark. The faster the car, which is to say a car with higher energy, the longer the skid mark it can make. Let's hang some numbers on this. A moving muon with an energy 10 times higher than its energy at rest can travel through about 2 meters of rock. A muon with 10 times more energy than that can pass through 20 meters, and of course a muon with more energy than that can go even farther. If a muon can punch through 20 meters of rock, what happens if you shoot it at a rock wall that's 10 meters thick? The muon punches all the way through and comes out the other side. In contrast, if you shoot that same muon at a wall that is 25 meters thick, it'll stop in the wall. It just doesn't have enough energy to make it through. But what about a 25-meter thick wall that hides a 10-meter wide cavern inside? A muon that passes through the cavern sees only 15 meters of rock. So, if you shoot muons with that amount of energy at a rock wall with a big enough cavern inside it, in some places the muons punch through, and some places they don't. So we could work with this. If we wanted to look for hidden rooms inside something, say the Great Pyramid, we should scan it with a muon beam of varying energies and see which muons punched through and which didn't. And if we scan it from different directions, we'll learn a great deal. Of course, particle accelerators capable of making muons are big, which makes it challenging to move them to scan large objects. So we need to find a natural source of muons. And luckily, Mother Nature is helping us out here. It turns out that a type of radiation from space called cosmic rays is exactly what we want, high-energy muons. Now, how those muons are made is the topic for another video. But back in 1936, physicist Carl Anderson and his graduate student Seth Nettermeyer discovered that muons created in the upper atmosphere rain down on the Earth's surface. These muons have a range of energies from very low to very high. We can't determine the energy of individual muons, but we can determine the spectrum of different energies. So this is how it works. Suppose this graph represents how many cosmic ray muons exist at each energy. Where the graph is high, there are more, and where it is low, there are fewer. To illustrate how this works, let's see what would happen if we scanned the detector over a giant rock with a room inside. We could scan any shape, but it's easiest to see what's going on in a cube. We can calculate what's the minimum amount of energy needed to punch through a solid cube. All muons with more than that energy will get through. If you put a muon detector on the other side of the cube, you can count how many pass through. However, if there's a room somewhere inside the cube, that means less rock, and therefore it's easier for muons to get to the other side. Lower energy muons can pass through, so you'll see more muons than you would if the cube were solid. So then what you would do is move your detector all around the cube and look at it from every side. And we see here how you would detect a room inside the cube. This technique of looking at many scans and reconstructing a three-dimensional image of what's inside an object is very similar to what doctors do when they make a CAT scan of someone's body. A CAT scan sends X-rays through the body, and the doctors see where more or less X-rays are transmitted. CAT scan stands for computer-aided tomography, and therefore the use of muons to look through big objects is called muon tomography. Muon tomography as a tool for archaeological studies was pioneered back in the late 1960s. A team led by physics great Luis Alvarez studied the Pyramid of Khafre, which is the second largest of the Great Pyramids. They looked for hidden room inside it, and they found none. A link to the paper is in the video description. More recently, a Japanese team used a similar technique to study the Khufu Pyramid, which is the biggest of the pyramids. While Egyptologists have long known about some rooms and passages inside the structure, the researchers were excited when they found a large and unexpected void. Now, Egyptologists don't think that the room holds hidden treasure. Instead, they think it's an architectural feature that relieves stress inside the pyramid. But it's still an amazing discovery. And again, I put a link to the paper in the description below. Researchers have used muon tomography to do other studies, like to look for magma inside volcanoes, to study the inside of nuclear reactors, and even to find out where the water can be found inside hurricanes. This is a fascinating topic, and some of my colleagues here at Fermilab are joining in. Alan Bross is working with a team who wants to do a very thorough scan of Khufu's Great Pyramid, looking for other undiscovered chambers. Mark Adams hopes to use the technique to scan the Temple of Kukulkan at Chichen Itza in Mexico. In both cases, they are using technology developed here at Fermilab as part of the particle physics program. It's a great example of how technology developed to solve one problem can be used in another situation. So that's how muon tomography works. It's a newer technology, and the scientists are still understanding the best way to use it, especially in the harsh environments at archaeological sites. It's a challenging problem, and I expect to hear about many discoveries in the future. All right, I don't know about you, but I'm pretty excited about muon tomography. It works way better than X-ray specs. The fact that technology developed to do particle physics experiments can be applied to archaeology is a fantastic example of cross-discipline collaboration. If you enjoyed hearing about this fantastic topic, please be sure to like, subscribe, and share because, well, that's what it's all about. It's an amazing illustration of one of my favorite principles, which is, of course, that physics is everything.